Hey everyone, FPS Chazza here. Welcome back to my nuclear stuff series. So today we are covering charged particles. We've covered the intro to particles and some basic radioactive mechanics. I think now we're ready to actually get into some radioactive particles today. So we're going to start with charged particles. Now that we've covered that stuff, we can now discuss this stuff. So radioactive decay is the process through which unstable atoms become stable by releasing excess energy, which is called radiation. This excess energy is released in the form of at least one particle, which will be discussed in this video. There are many kinds of radioactive particles, but we're only concerned with 5, which fall into one of 2 categories: charged particles and neutral particles. So this video will be charged particles, and then there will be a separate video for the neutral particles. The charged particles consist of alpha particles and beta particles, and the neutral particles consist of photons, neutrons, and neutrinos. 3 of these we explicitly discussed in the particles video: photons, neutrons, and neutrinos. One we implicitly discussed: beta particles. However, we did not discuss alpha particles, so let's start there. So an alpha particle is essentially, it's 2 protons and 2 neutrons. So I'm going to draw this nice and big. So we have 2 protons and 2 neutrons. This makes up the alpha particle. So this is basically, if you remember from earlier, this is a helium atom. It just doesn't have electrons. It's without electrons. So if you remember, this is now an ion of helium. And this charge is +2 because there's 2 protons but no electrons to cancel out their charge. So this has a charge of +2. And this is what makes this a charged particle. And this is also ionizing radiation because it is an ion, and it will make things ions because it will steal electrons from them. But we'll get into that in a second. So, besides the fact that this is the largest radioactive particle, basically, since it has this charge, it means it's very interactive with matter, which is what. So, although this particle is huge, it really doesn't. It's not really too big of a danger, but that's kind of there's like a double-edged sword of that. It kind of depends on the situation and what makes this dangerous or not. Let's just imagine, if you will, that you have like a piece of steel, and you have a bunch of magnets, north, south, north, south, north, south. Let's just say you were to toss this piece of steel through here. So you would throw it through here, and it'll bend up this way because of that magnet, then bend down that way, then bend up this way. So that's the same thing that you can think of happening with the it's the exact same thing. Electricity and magnetism are one and the same. This exact same effect is what's happening on the atomic level. So this might not make sense at first because atoms in nature, in your body, the atoms in your body are not ions. They are stable atoms. So how can this polarization effect happen? Well, it's because the atom is it's mostly empty space. I don't know if you're aware of this, but let's take a football stadium, and yes, this can be either American football or international football. The pitch is the same and the field is just about the same. So I'm going to go with American football here, whatever. And then you got your end zones. Yeah, there you go. Okay. 50-yard line right here. So to imagine how much space there is, you can say that at the 50-yard line here, or center field if you're talking about soccer, football, international football, not American football, the nucleus of the atom is the size of a golf ball. Which sounds crazy, but it's real. Well, okay, so the analogy hasn't come, excuse me. So the nucleus is the size of the golf ball, and that's right here in the center of the field. And then the electrons are all the way out here, in the stands. That's how much empty space there is in an atom. So we're made of mostly empty space. So in our analogy here, replace the steel. Okay, well, I didn't here. This is the alpha particle, denoted by the Greek letter alpha. And so in our analogy here, just replace the steel with an alpha particle, and then replace these with these magnets with nucleuses, with nuclei. Excuse me. Replace these with nuclei, and there you go. So the atom in itself, the atom here. The atom itself is a neutral thing, but since there's so much empty space, this alpha particle doesn't care about these electrons out here. All it sees is this nucleus, really. So the alpha particle is what comes through here and then interacts with this nucleus. It gets electromagnetic effects. So that's what makes the alpha so terribly not good at penetrating things, is that all these things really take a lot of energy off of it as it goes through. So it gets attenuated very quickly here. So it won't. Here, let me just move on, so maybe this will make a little more sense. So, for example, a piece of standard printer paper right here, or a few dead skin cells, so the top layer of your skin, is all that's needed to effectively stop alpha particles because of this. So even though there's like, your dead skin is not very thick, remember the Avogadro's number, how many atoms there are in a certain mass of something? So like, this piece of paper is so thin, but I'm sure it's like trillions upon trillions of atoms thick or something. Maybe not that many, but it's pretty. There's a lot of atoms in there, so it's this alpha particle is interacting with a lot of things. So on the other hand, if you were to ingest alpha particles, that's when they become really dangerous. At that point, they're considered to be 10 to 1,000 times more damaging than beta particles or photons, which we're going to talk about later. And photons are the most considered like generally the most damaging form of radiation. So the reason for that is because you have these dead skin cells out here to protect your body from the alpha cells, but if you breathe it in, you don't have that same luxury in like your lungs. So these things will just go all throughout your body. And you can imagine this as like a wrecking ball. Just, take your, your DNA strand. This is going to be a very bad drawing of DNA here. This is terrible. There's your DNA here. And this isn't a very large structure, so you can imagine this alpha particle just coming through here and just like smashing it, just breaking it completely. And that's what makes radiation damaging to people, is that it damages your DNA, which keeps your cells from being able to reproduce. But we'll get into that later. That's what makes radiation damaging. So only the heavier elements will emit alpha particles, and we discussed this in another video with uranium. Uranium is a alpha emitter. A lot of its isotopes will decay through alpha. Alpha decay got 235 and 238. They both decay through alpha if you just let them sit there. So remember from the alpha decay, so we have uranium 238. Let's go 238 and then 92. So this is our atomic number, and this is our Z number, our proton number. So when you alpha decay, the alpha has 2 protons and it has 2 neutrons. So your Z is going to drop by 2, and your atomic number is going to drop by 4. So that will take you down to that'll take you down to thorium 90 234. And we bring that up on the periodic table. You can see that. I hope you can read this. So we have uranium 92 and then thorium 90. So the proton drops down in 2, and then this the atomic weight that's listed here is natural abundance. I don't know if I've described natural abundance, but that's just an average of all the atomic weights as they appear in nature of all the isotopes. That's basically what that is. So you'll get your alpha decay, and this is what will happen. You'll drop your atomic number by 4 and your proton number by 2. So you'll get this thorium plus an alpha particle that just goes out to wherever. So that's what you'll get with the alpha decay. You might get a gamma or some neutrinos to accompany that. But probably just the alpha. I'm not sure about the gamma part there. Okay, that about does it for alpha particles there. So stay tuned, guys. Next time we'll cover beta particles and finished up charged particles before heading on over to the neutral particles. See you guys later. Good hunting.